Hello and welcome back to our final video in this brief series on exponential models. In this video, we are going to discuss Newton's law of cooling. Now, Newton's law of cooling was developed by Sir Isaac Newton in the late 1700s. He noted that the temperature difference between two bodies is proportional to the rate of heat loss. The model appears as follows. We have capital T of little t is equal to m plus the quantity T naught minus m, then that quantity is times e to the negative kt. Now capital T of t is representing the temperature at time little t. M in this model represents the temperature of the surrounding medium. T naught is the initial temperature of the object, or the temperature at time 0. K is the rate of cooling. We've already factored out the negative for this. And T is time. Now, ideally, the temperature of the object will eventually match the temperature of the surroundings. Under this consideration, we will have mathematically a horizontal asymptote at y equal m for this law. So the graph of cooling an object would behave something similar to what we see on the right. So here we're saying that as we increase the rate of cooling for the object, then the curve itself gets closer to that surroundings temperature very, very quickly. And this is the goal of the animation. So here we can see that as the K value decreases from 3 to 2.7 to 2.4 to 2 and stuff like that, we can see that the curve bends a little bit more away from that horizontal asymptote at the temperature of the surroundings. So as we increase the value of K, as we see here, the curve drops sharply and the bend occurs as we get closer to that horizontal asymptote. And this is essentially what Newton described with his law of cooling, is that the larger the cooling rate, the quicker it's going to get to the temperature of the surroundings. Thank you for your time and attention.